So welcome everyone. It's my great pleasure to welcome you to this latest IIT seminar. So today we have Maxime Clenet from Sherbrooke, who's going to speak to us about metapopulations. So take it away, Maxime.
Yes, thank you for the introduction. So I'm really happy today to present my work. So I would like to first say that it's an ongoing project. So if you have any insight or you want to discuss about something, I will be really happy at the end of the talk to talk about the work. And I really also love this initiative of this seminar series. And so I'm really happy to present my work today at the seminar, to be on the other side. So first, I would like to give a small quote of Ilka Ensky, that was of the pioneer of the metapopulation theory. And so he said that mathematical models of metapopulation are constructed in the hopes that they will clarify our thinking, reveal unexpected and significant consequences of particular assumption, and lead to interesting new predictions that could be tested with observational and experimental studies. And what I want to highlight here is that, so I am like a theoretical ecologist, but I think that I'm trying more and more to look at what we could do with observational and experimental studies, and I think that there is like a really beneficial cycle between a theoretical ecologist and empirical ecologist. So to give you a little bit of context, so today habitats are fragmented. And we know that the interaction between species and their habitat are a key, are essential for the persistence of the species. And so we know that habitat fragmentation is one of the main driver of biodiversity loss. And we also know that we can consider habitat fragmentation, but we can also think about seasonal fragmentation. For example, when we think about, for example, aquatic species, depending on temporary ponds, depending on, for example, the wet season and the dry season, where ponds can be full or disappear. And so I think it's really important to be able to understand this fragmentation, and metapopulation theory is one of on the way to be able to understand this interaction between species and their habitat. And so I want to put forward today two type of habitat descriptions. The first one is habitat fragmentation, that can be caused by natural phenomena, for example, fires, or when we think about ephemeral patches or land use by humans, and also seasonal fragmentation. So the fact that some species rely on the seasonally available habitat. So when we think about birds that migrate between winter and summer, they have different habitat, and this migration is essential for their persistence or like survival. But when we think about habitat, we think a lot about habitat in a static way. But habitat is today changing really rapidly. So if we look at so here we add an example of a forest in Cambodia, and we see that in 20 years, it has changed a lot due to the land use by human. And these changes that occur more and more rapidly has like a really strong impact on the species persistence And it has also like a strong effect on the movement of individuals or disease or, for example, perturbations. So from a theoretical point of view, metapopulation models are created to help us to understand the relation, the interaction between a population and a given habitat, how this population can persist. And we mainly look at a stationary analysis. And so I think that now it is more and more important to take into account the temporal dimension of habitat and also ecological network in general. And so I'm trying to look at two different fundamental questions. The first one is how does the temporal structure of the landscape, so in the case of habitat fragmentation or seasonal variation, has an influence of the population persistence? And the second one is it possible to find some temporal metrics that will give us some like better insight into ecological system that you won't be able to get using only a stationary metric? And so in this presentation, I will try to give you some insight about which kind of metric we could use to get a better understanding of a metapopulation in the case of a changing habitat. And so to be able to explain you this theory, we have to start from the beginning. And so metapopulation theory was one of the first model of metapopulation theory was proposed by Levins at the end of the 60s. And so it's a simple model to explain the dynamics of a species in a patchy environment. So you consider that you have an habitat that is discretized by different patches. You think you have an infinite patches and an infinite number of patches that are fully connected. And then you consider mainly two ecological processes. The first one is colonization. So the fact that if a patch is occupied, it can colonize empty patches. And you have a second ecological processes, which is extinction. So the fact that occupied patches can become extinct. And so when you want to study the proportion of occupied patches in function of time, which is denoted by P of t, then you can derive a simple ODE, which is given by this equation, which is a logistic model. So you have an analytic solution and you know the behavior of the model. So you can either have a convergence to a fixed point in the case where the colonization rate is superior than the extinction rate, and the species goes to extinction, so PT converges to 0 in the case where the extinction rate is superior than the colonization rate. So you have here a simple model that explain that take into account two ecological processes to look at a population in a really large habitat. But you don't really consider that this habitat is in fact is in some sense finite, and the fact that you don't have like a complete connection between the patches in the landscape. And so in order to study this kind of model, Ansky and collaborators try to take into account the fact that every patch are not connected to each other. And so in particular, they wanted to study the metapopulation of butterfly in the Åland Island in Finland. So here you have a given habitat where the butterfly can be. And so you will consider that you will see this habitat as a bunch of different patches, and these patches can be of different size, and they can have a different distance between each other. And so you want to understand in which case this butterfly will be able to persist in this kind of habitat. And so to model this, you don't consider now the proportion of habitat patches in function of time, but you will look at the probability that patch I is occupied at time t. And so you will have a system of n equation if you have n habitat, which is given by this system of equation. And so the first term, the colonization rate of empty patch I is given by this equation that depends on C. So the colonization rate of the species, AJ, which correspond to the size of patch J, and F, that is a dispersal kernel function. In the case of the Ansky model, they considered mainly an exponential function. And you have dij that correspond to the distance between the different patches. And so if there are many patches close to patch I, then the colonization term will be really, really strong. And on the other side, you have also the extinction rate of patch I. And this depends on E, so the extinction rate of the species, and also it depends on the size of the patch. So if you have a really huge patch, then the extinction rate of this patch will be smaller. And if you have a small area, then the extinction rates will be bigger. And so when you look at the dynamics of this kind of model, in fact, you can have two kinds of behavior. The first one is the species persist. And so the probability of occupancy of each patches converges to a positive value. And on the other side, the second behavior that you can have is the extinction of the species. For example, here I considered two different connectivity matrix, so two different landscape. And we see that here, all the probability goes to 0. And so it means that the species cannot survive. And so we want to understand, is it possible to get a criteria to understand in which case the species will be able to persist and in which case the species won't be able to persist. And so in order to do this, you can just rewrite the model in this form, and you can, and the important term here is the matrix M here. So the matrix M, the first observation is that the matrix M only depends on the landscape. So it doesn't depend on the properties of the species. And so this matrix M is known as the landscape matrix. And what you want to know if the species will be able to persist or not, you look at the spectral radius of matrix M, and you will be able to know if you have a positive equilibrium if the spectral radius of matrix M is superior than E divided by C. And so this largest eigenvalue of matrix M is known as the metapopulation capacity. And so you have a really simple metric in some sense to know if the species will be able to persist in a given landscape. But in our case, we want to take into account the fact that habitat is changing. And so in order to think about ways habitat is changing is to consider a new mathematical object, which is temporal network. So a temporal network is a network where connection between nodes change over time. And so we see that we have, imagine that you have like here, you have 3 different patches, then the connection between the patches can change over time. And you can also consider that the strange, that are related to the weight of the connectivity matrix can also change over time. And so the sizes of the patches can also change over time. And so temporal network are a mathematical object that is really different to static network. And here I want to highlight a small example. So imagine that you have three patches, and you want to see if individuals can go from patch I to patch K. And so in the static network case, then it will be always possible to go from patch I to patch K. But in the case of a temporal network, then the timing of connection becomes super important. So here at time t, if you have a connection between patch I and patch j, and at time t+1 patch j and patch k, then you will be able to have some individuals that go from patch I to patch k. But on the other side, if you inverse the timing of connection between the patches, then you won't be able to have any connection between patch I and patch K. And so the analysis of temporal network becomes more complex and more intricate. And you have also this thinking of directionality. And so a way we think about this temporal network is the fact that we have some snapshot of a given habitat. For example, we have a snapshot of every year, and so we get different layers of habitat every year. And so when we want to study this different snapshot, a way to do this is not to look at a continuous model, but to look at a discrete model, which is used a lot in epidemiology in particular. And so you want to you are still looking at the probability that you have that the probability that you have that the species is occupied at patch K here, and it still depends on the vector of extinction rate that depends on E and the size of the patches, and also a connectivity matrix that I defined by S. And so what is interesting with this model is that if you look at the equilibrium of the system, it is related to so one of the equilibrium of the system is 0, and it is an unstable equilibrium. So you will get the same threshold conditions than the continuous model. And so when you want to study the behavior of this model, you want to know if the species will be able to persist or not, then you will recover the same condition as the continuous model. But what is interesting in this discrete time model is that now we can assume that habitat is changing at each snapshot. And so you can consider that the size of each patch I is changing, and you can also consider that the distances between the patches is changing. And so now you can rewrite the same model, but at each time t, the parameter, so the connectivity matrix and the vector E here will be changing. And so we define as the temporal metapopulation model, and we want to get information of the dynamics and behavior of this system. And so a way to do this is to think about a multi-layer network. So multi-layer network are mathematical objects that are more and more used in ecology to represent a lot of different systems. And in particular, you can think of our case, the case where, so a multi-layer network is a network where you have different layers, and in each layer you have a network. And so you can have an intra-layer connection, so connection between the network in each layer, but you can also have an inter-layer network. So you can also have connection between the nodes in the different layers. And so when you think about multi-layer networks, you can think about the temporal networks. So the fact that here you have different layers for each time, it is our case, but you can also consider, for example, that each layer is different patches, and you can have and you can consider, for example, a community in each patches, or here you can also consider that you have different interaction types. So for different interaction type between species. And so here you will have two layers and different interaction between species. And so when we want to study this model, we can use, in some sense, the multi-layer framework. And this was done in epidemiology, and so we try to do the same. And so in order to do this, first you have to think about, okay, so imagine that you have a connection. In the case of a static network, imagine that you have a connection at time t between I and j. And so the first thing is that now you have two layers, and you want to represent the dynamics between the layers. So the fact that you have a directionality of the dynamics. So you will go through the layer 0 to big T. And so to represent the extinction process, it is represented in the ordinal coupling. So the fact that the extinction process has only an impact on the node itself, on the patch itself. And to represent this, so you can represent this by an arrow between the same node in two different layers. So the fact that you will have an extinction process between time t and time t plus 1. The second thing that you have to consider is known as the non-diagonal coupling. So it's the fact that you can have connection between two nodes that are different between two nodes in different layer, and the two nodes are different. And so we can use this kind of connection to represent the colonization process, where individuals here, for example, can go from patch I to patch J. And so to represent this, you will create a link between here patch J at time t and patch I at time t plus 1. And so you will have a colonization process between these two layers. And so maybe to sum up this, you can represent the temporal metapopulation model as a multi-layer network, where you take into account both the colonization and extinction processes. And so really a way to think about this is the fact that instead of having a dynamics in one layer in a network, the dynamics is just going forward through the layer. And so the extinction goes from here patch blue to patch blue from like the red links here, and the colonization processes goes from patch blue here and patch green here. And so it is represented by this matrix. And so what we have here is that imagine that you have big T different snapshot. And so you want to get information on the dynamics from layer 0 to layer T. Then the trick here is to do a projection in the bigger space NT. And you want to understand the world dynamics in the space NT time NT. And so you will consider that this series of snapshot will be something that is periodical, and you want to understand in one way, in one instance, what is happening in the series of snapshot once one at the in one way. And so if you do this, you can do a mapping to do this, and then what you get at the end is that you recover a really large matrix. M here, it is a block matrix where each entry here of the matrix is a block matrix that represents each snapshot. And so here you have snapshot 1, snapshot 2, etc., and this is known as the supra-adjacency matrix. And what is really important here is that if you want to get information on the temporal, the persistence of the population, where you have this different snapshot, you can define what we call temporal metapopulation capacity, and is defined by a threshold condition. So if you look at the spectral radius of this matrix, if it is superior than 1, then the species will be able to persist. If it is inferior than 1, then the species won't be able to persist. So I want to give you two small perspectives on what we can do with this kind of methods. So the first one is to think of a migratory network of a species. Here, the swallow, where the habitat is changing over the season. And so in winter, species are in the south. In summer, species are in the north. And you want to get information about in which case the species will be able to persist. And so I created a toy model where, so in spring, species goes from south to north. Then in summer, you don't have any connection in the patches, and in autumn, species go back to the south. And what is important here is the fact that if you consider that that species has only access to one habitat, then you don't have any connection. And so the dispersal, the migration of the species become, in fact, essential to the species to survive. And we want to understand, okay, in which case the species will be able to persist. And so we can do a first dynamics where we consider a given colonization rate of the species. And so we look at the probability of the patches in winter in red, and the probability of the patches of the occupancy probability of the patches in summer. And we see that in this case, the species, the species cannot persist. But if we increase the colonization rate, then in this case, the species can persist over the season. And so we want to understand, okay, so does our new metric give information about the persistence of this metapopulation? And so if we look here on the blue curve so we increase the colonization rate, and we look, okay, in which when do we cross the one line, so the threshold where the species can persist. And so in fact, when we look at the persistence of the species, we see that we really catch when the species is able to persist over time using the thresholds that I gave earlier. Now, I would like to give you a second perspective on more seasonal fluctuation in random landscape. And when we think more about, like, for example, aquatic species that depend on a temporary bounds where, so you have different seasons where a species cannot disperse all the time. And you can also think about in different season species, you have some seasonal dispersers that can be present or not, and so you can have a seasonal connection also in the landscape. And so a way to model a given habitat is to use a random fragmented landscape, like to use in particular random geometric graph. And so a random geometric graph in the case of the metapopulation model of Ansky was studied in a paper 10 years ago by Grilly Barabas and Alesina, where they looked at, okay, so if we consider that the habitat is a random geometric graph or a Euclidean random matrix, you want to understand in which case the metapopulation will be able to persist. And so using tools from a random matrix theory, they looked at they gave some information about, okay, so the largest eigenvalues they were able to recover information on the largest eigenvalues of this matrix M. And so they were able to deduce some really interesting results. So the fact that hubs are super important to the persistence of the metapopulation, and also that the density and the shape of the dispersal kernel can play a really important role to know the persistence of the metapopulation. But they only consider, in fact, the case of a static habitat, but it can be in really large dimension. So now consider that habitat patches are of equal size, and so you use a random geometric graph. Which is in fact, so to define a random geometric graph, you take a square, for example, of a given size. Here we took a size 10, and then you draw all the nodes from a given distribution. So here, so in fact, you draw the coordinates from a uniformly distribution from 0 to 10. And then you define that two nodes are connected if their distance is less than a critical migration radius that we define by R that you can choose. And what is interesting with this geometric graph is that you get what is known as a percolation threshold. So the fact that when R become superior than a given percolation threshold, then you get a giant component. So here, if we look at this, so here we have the same random geometric graph, but you have a different critical migration. So here we see that we have different small hubs that are not connected. But if you increase R, then you will get to a point where you get this giant connected component, but the fact that you can start from every patch, you will be able to reach another patch, like any patch, in fact, in the graph. And so we wanted to look at if you consider that this radius is varying over time. And so the ideas was studied in a study by Palamara and collaborators. And so they defined this migration radius by this function. And so when you look at this, it goes from 0 to A, where A is the amplitude of seasonal fluctuation, and W here is the frequency of the periodic cycle. And so you can choose if you have a lot of cycle. And we wanted to look at, okay, do we have a difference between the case where you just have a constant static habitat, and in the case where you have a seasonal changing habitat, where you have the connection between the nodes are changing over time. And so when we look at the graph here, I looked at the temporal metapopulation capacity, and we see that when we increase the amplitude of the seasonal fluctuation, it goes from point where the blue curve here correspond to the static case, the orange one correspond to when you have like one period of time, and so we see that when we increase some given value, which is here given by the percolation threshold, but for other example, it is not so smooth here. The static case get a better persistence here, for example. And so what it means and what is interesting here is that you will, when you compare the static and the time varying case, you will get somewhere where the R will be above the percolation threshold, and then you will have a lot of connection, and then you will go back to 0, but still you stay a lot in the case where the percolation threshold is inferior to R, then the species will be able to persist. And so seasonality here might be to keep, in fact, the seasonal fluctuation might be really important for the persistence of the metapopulation. And so to conclude my presentation here, I wanted today to highlight the fact that both seasonal variation or human activities are really put forward the fact that you have to consider today's temporal dimension of ecosystems, both for changing habitat, but also I think for changing interaction between species, for example. And so I think it is also a need for both empirical and theoretical ecologists. And I would love in the future of my research to be able to apply those theory to empirical data. And so today I presented you a theoretical framework to look at temporal dynamics of metapopulation, and it is a lot inspired by a physicist work, mainly for epidemiology. And so I gave you a new matrix, which is a temporal metapopulation capacity, which is not so simple metric, but a metric to quantify the ability of metapopulation to persist in the case of, for example, we could, so today I gave you 2 examples in the case of periodic dynamics, so the seasonal habitat dynamics, the migration one, but we could in the future look at, for example, the role of ephemeral habitats. And so for longer term perspective, I really love to extend this theory from metapopulation to metacommunity ecology, because when you add interaction between species, maybe it will be more complicated, and you will have a really, you will be able to look at different scale. And the second point is that so today I looked mainly at time varying habitat, but I think it might be also interesting to look at time varying interaction network, where the species interaction can have a strong impact on, if you consider, for example, for the case of migration, the case where a species arrive one at a time in a given habitat, where the connection, the interaction will evolve over time. And so I wanted to conclude the presentation also by a quote in this paper that I found really interesting. So in the 20th century, classical Newtonian physics gave way to Einstein's theory of relativity, with the recognition that time is not simply a fourth dimension orthogonal to space, but a relative matrix inherently intervened with space. Ecology now has an opportunity to build a similarly integrative spatiotemporal framework. And so this paper in Ecology Letters by Volkovich and collaborators, which is really nice. And so thank you for your attention. I would like to thank my two collaborators in University of Sherbrooke, so Guillaume Blanchet and Dominique Gravel. And if you have any question, I would be really happy to answer.
Thank you so much, Maxime. So anyone has any questions, the easiest way to do it is to raise your hand in the chat. So if you just click on the React part, there's a raise hand button if anyone fancies putting a question forward. I think they're all applauses so far. Just looking at the participant list. If our people are just figuring that out, and one question I wanted to ask about the swallow example. So this looked like it kind of was beginning to come from some empirical data. Is there a way of linking back your model and its predictions back to this empirical data, or is it more just a motivating example, do you think?
For the moment, it is just an example. So I think that the model that I wanted to show you is more like a way to say. So if maybe I can go back. So this model, this like sort of small toy model, is more like a way to show that dispersal is something that is necessary for the species to survive. And I think that's a point that is really important. But I really looked, in fact, at like a small toy model, and it was really also good to highlight the fact that the temporal metapopulation capacity is working, and it also gives more information than the static case. But in the future, I would love to be able to look at this kind of network where you have in fact a lot of data, and so yes, that's a really good point in the future.
Oh, thanks. Giza, I think you're up first.
Thank you. It was very interesting. And is it my right understanding that you always consider a cyclic environment?
Yes.
Yes,
so,
because you have to take into account the whole cycle and then consider the leading eigenvalue of matrix, if I understand you correctly. It would be very interesting to understand the same thing on a long-term fluctuating environment. I don't know how, but I don't know whether you have think about it.
Okay. So I think I didn't. I would like to. Okay. So the model is inspired by epidemiological model, and in fact you have some condition to consider in the model. And so in my case, I consider cyclic or periodic dynamics because it is in fact like a mathematical condition that you have to consider to get the convergence of the model.
Yes.
And
yes.
so to ensure that you have yes, an asymptotic solution, you have to consider this periodic boundary. But in fact, what they in epidemiology, they looked at non-periodic system by looking at the case where, since you consider that T is something that you can choose, then you can choose it as long as you want. And so you will be able normally to look at the model in like a global generality, since T can be
Okay.
really, really big.
Okay.
You, Chris?
Yep. Thanks, Maxime. That was a really cool talk. So I'm wondering, maybe a simpler question than Geza's. You moved from the continuous time to discrete time at some point. Is there some limitation that you can't do this in continuous time, or like how could you like make that connection?
So so the continuous time to discrete time is a really good point. I think the two model are different, so you don't have to. It is not the fact that you like discretize the continuous one to get the discrete one. It is two distinct model, and I think that the discrete one is mainly related to the fact that you are, when you go to the field, in some sense, you consider that you get only some snapshot of the habitat, and you don't have a continuous version of the habitat. And so then the discrete model has a lot of sense. But I know that there are some ways to consider the continuous model and to take into account the fact that the matrix is changing, and you have also a theoretical relation between the two models for some condition on the matrix A, but I didn't look deeply into this relation for the moment.
Oh, cool. Thanks.
I guess slightly following on from that, is it then possible to have in the continuous time sort of your multi-layer networks without that discretization? Do you end up with essentially a function that travels through time rather than this sort of array that you were describing just then? Or maybe I've totally got the wrong end of the stick there. But do you see what I'm getting at? Or I can have another attempt.
But I think that if you consider the continuous time, you will have something that is different, probably. But I think that you will have to think about the model in another way. Like, to think about multi-layer, it is in some sense perfect because you consider that you have this discrete layers. But in the case of the continuous model, then it will probably make less sense to consider this discrete way of looking at your habitat snapshots.
Yeah, I mean, I find multi-layer networks really intriguing, but I guess you actually said many times in your presentation as a representation of describing what we've got. I think what was nice about this talk is that you had an analysis that actually used that representation to go off and do something useful. And I wonder how many other sort of results like that do you think there are that can be pulled out from these multi-layer networks? Or are they really just a way of describing what we've got, should we say?
So I think that could be really good to. So here we look at habitat that is changing over time, but you could also think of so interaction network, for example, that are a lot used in the case of multi-layer network, and you could also consider think of like interaction in a community that is changing over time. And so the energy that goes from species to the other is also changing over time. And then you want to understand maybe if you want to get some result on the coexistence in a given community that is where interaction are more intricate and more complicated, that could give you something interesting probably. But I think to consider this temporal network and multi-layer network is something that that can be really good to do in the next years, I think.
Giza.
You had a figure in which when the eigenvalue crossed the one, then something started to grow from zero. And show please again and tell me what was the vertical axis, what was the quantity which started to grow. This was it. Okay.
Okay. Yes.
Okay. What is it?
Okay. So here, in fact, so the blue solid line here is the temporal metapopulation capacity. So when it crosses one, something grow.
Yes.
But I didn't describe what it is. So, but it is so. What I look at is, so I wait long enough to the system to converge to a given in fact, it doesn't really converge to its equilibrium, but I just look at the mean of like the probability at some time to see if the species is still present or not. And so if the species goes, since you have two behaviors, the case where the species can persist and the case where the species goes to extinction, then if you wait long enough, then the species will go to extinction. And when you compute just the sum in some sense of the probabilities, then you will be able to see that the species is extinct or persist.
But I don't really understand such kind of behavior is well known when we start from a single individual and a clone either persists and grow infinity or dies out. But here, what was the initial conditions?
But I think that you can, you have in this case a global stability result, so you can take any initial condition, you will converge to.
Okay, but then there is a probability of for extinction, yes. But then if it doesn't go extinct, then, well, my expectation would be that if there is a possibility of extinction, then it will happen sooner or later. So the long-term survival would be zero. No?
So here, like, okay. So if I understand correctly, what you mean is that if we go back to the model of Ansky, so if I completely understand what you mean is that, so in the case of the model of the metapopulation, the spatially realistic metapopulation model, you look at the sort of you get a quasi stable like equilibrium in the sense that you are not looking at the Markov process that is behind the model. Because in the case of the Markov process, if you consider a finite number of habitats, then I agree that the probability of extinction is almost surely equals to 1, because at some point you would go to extinction. And and in this model you have the same. You are looking at at the quasi-stable equilibrium, the quasi-stable. You are not looking at the Markov process behind the model that is going to extinction in any case.
Okay, thanks. I will read your paper and then I will understand.
Okay. Thanks a lot. Are there any final questions from anybody? Otherwise, we've hit the hour, and I'll round it to a close. Nope, looks like no. So thank you to everybody for coming. In fact, thank you, Maxime, for a fantastic talk. This is going to be the last one of this particular series, but we'll be back sometime in the autumn. So look out for an email for that. And we'll see you then. Thank you. Bye.
Thanks.